Good afternoon, everybody. I hope you can hear me. Welcome to today's ECCA webinar on colour measurement in the coil coating industry. We've got a very interesting presentation for you this afternoon. In terms of what we're trying to achieve, the main purpose really is to increase the understanding of how colour is measured and used in the pre-painted metals industry. There are customers of pre-painted metal on the call, and so we're trying to help them understand this very important aspect of the industry. And in doing so, we will explain how colour is perceived, the different techniques that can be used to measure colour, and the importance of colour matching within the industry itself. Before we get into that, just a quick reminder of our standard disclaimer for these webinars. The team has prepared a set of information which I'll go through over the next hour or so, but we can't accept any liability for what you choose to do with this information going forward. I'm just here today to introduce the webinar. My name is Terry Goodwin. I'm the Sustainability Director of ECCA. The three ladies you can see on the screen there will be doing the bulk of the presentation. We have an excellent combination of both experience and expertise in colour and the coil coating industry today. Virginia Vaccaro has a PhD in computer science, which is applied to digital colour imaging. She's the colour expertise manager with global responsibilities within Becker's Coatings, one of our leading paint suppliers in the industry. The other two is Dr. Marina Latza and Cressida Katsara from Elval Colour, a highly regarded coulter. Marina has a PhD in chemical engineering and has been responsible for quality control and R&D within Elval Colour since 2011. And Cressida is their colour specialist. She has a PhD in colour science and digital imaging, which are a result of her studies here in the UK. So a very good team. As I said, they'll take you to the detailed content once I finish the introduction. Next slide. We're going to talk about the importance of colour consistency, a bit about colour theory and measurement, what are the factors influencing colour change, how you should use colour standards and how they drive the overall specification. And as I said earlier, we'll come back to Q at the end. So if I just start with a brief overview of the importance of colour consistency in the industry. Well, I'm sure you all recognise that colour is one of the key characteristics of pre-painted metal products. Others, of course, include durability, flexibility and corrosion resistance. However, colour is often used in conjunction with gloss, appearance and surface texture to differentiate the product. And you can see some examples of the gloss, iridescence and texture on the screen. Ultimately, it's the coloured surface that is seen by the end user and the market. Colour and fit of the pre-painted metal product is often the key differentiator, and you can see from these examples how well colour has been used to create a very aesthetically pleasing building or in the centre there, domestic appliances. If you want more examples, then please visit our website. However, within the industry, sometimes colour is intentional, as you can see on the left-hand side, where the architect has specified that graduated green as you move up the building. Unfortunately, sometimes the supply chain doesn't quite work as it should. And on the right, you can see some poor colour matching and some very obvious difference on that wall of the building. The next slide also gives you some other examples of how the supply chain has failed to deliver an adequately specified colour. And this obviously leads to dissatisfied and unhappy customers at the end of the supply chain. The importance of getting colour matching right, I think, is very well demonstrated by this slide. If you look at the left-hand side, the cost of the paint may be up to €1,500 as you move through that supply chain. So the value of the product increases. So sandwich panels, when they go on the building, can be very expensive in terms of euros per square metre. And the cost of rectification, of course, increases dramatically as you have to deal with a remedial action on the building. So that's just to give you a very brief introduction to the importance of colour matching and why it's so essential to get it right through the supply chain. I'll now hand over to Virginia and the other members of the team to take you through some very clear explanations of colour. Virginia?
Yes. Good afternoon, everyone. Actually, I will let Cressida start.
Thank you very much, Terry. Thank you, Virginie. We'd like to start this part talking about color with this famous quote: "Color is in the eye of the beholder." Now, this couldn't be more true. Would you agree, Virginie?
Oh, yes, totally. Especially when you know how much the phenomenon of color is subjective to each one of us, and how much the way we interplay with the light and with everything that we perceive will create this unique signal. And also because it is going through a very long journey within our brains through some neural network to give the final interpretation, so that from the initial object we are looking at, then it goes into the eyes, and then the brain, it makes it unique. And that's the reason why it's so important to understand how it is that we see in color, and what is the interaction between all elements. And before doing that, we need to start with the very basic principles, which is understanding that we've got three elements that enters in action when we speak about color. The first one, obviously, is light. And if you don't have any light, you don't see anything. In a dark room, everything is dark. It's obvious. This light comes and strikes the object, and this is what makes the color possible, because without object, there is no color. But there is no color if you have no observer. It can be the human eye, it can be a camera, or whatever, a visible sensor that makes the color real. And let's dig a bit more now into these three elements to understand what role they play in the color stimuli creation. And let's go in the light source part. Cressida, over to you.
Thank you. Well, a light source can either be natural or artificial, and it is characterized by the spectral power distribution, which is essentially the amount of energy that is emitted by that light source at each wavelength that is visible to us. Now, light sources have been standardized as a set of SPT tables, and they are called illuminants, and they represent typical light sources, such as daylight. For instance, on our left, we can see a graph of the illuminant D65. Now, D65 is a set of numbers, a table, that represent average daylight. On the other hand, on our left, we see an artificial light source, which is redder, illuminant A. Now, comparing the SPT of D65 against the illuminant A of a tungsten lamp, we see that a daylight illuminant emits much more white light. It has much more energy towards the lower part of the spectrum, whereas illuminant A is a warmer, redder light.
Okay, great. So that means in the end, we can wrap up on the light part, saying that it is a distribution of energy within this visible spectral range. And this energy comes and strikes the object. So what happened with the object now? Let's have a look to this specific dog, let's say, and maybe the red part of it. How can we characterize it? The way we do it is by looking at its behavior in terms of absorbing this energy and reflecting this energy. And here, for example, we can see that it is absorbing all the violet, blue, green, and so on, and it is reflecting all the orange and red, and that is what makes it red. And actually, it comes from the pigment that is composing the matter. And depending on the pigment, we will not absorb or reflect the light the same way. So with that, we can directly and completely characterize the color of an object. The combination of the light and the object reflectance characteristic would then gives this color out of the object that arrives to the observer. So what happens at the observer level? Let's do a bit of anatomy here, even if we're going to be a bit quick. I'm not a doctor in medicine, at least. And let's speak of the eye by making a comparison with the camera, because maybe you know better the camera than you do the eye. Just keep in mind, though, that the eye was there before the camera, and the camera has been built to try and reproduce the eye. But anyway, if we have a look at the way the eye is done, we've got an objective part, a lens part that allows all the light to enter into the eye. And that back part of the eye, we've got a sensor part, which is the retina. And on this retina, we have kind of pixels, but of course it's not pixels. And these specific visual cells are rods and cones. And we've got these two types, rods that are everywhere on the retina and cones that are in this very particular center part of the eye, where we have three types actually that enables us, in the end, you will see how to see in color. And there are cells, so they activate at different level, meaning if you do not have enough light, only the rods will activate. And they are very sensitive, by the way, because even in a room where you have a very, very small light, you would see everything. In black and white, yes, but you see everything. As soon as you've got enough energy, then, you see all the color and all your cones activate. But if you have too much energy, then you start saturating them, as you would with the camera, by the way. That means that if you look at quite saturated or bright sample, and you look at them a bit too long, at some point you will not see anymore the color. You will see something very strange because your cones start behaving very strangely. And maybe, Cressida, you can even go a bit deeper into that. What happens if there's something wrong with our cones?
Well, I'm glad you mentioned that. We don't always take it into account, but it's true that a small part of the population is born with 2 instead of 3 cones. Now, according to which type of cone is missing, they fall into different categories. Either way, they perceive their range of colors very differently as opposed to a color normal, someone who has all 3 cones in their eyes. So this is something we need to keep in mind. Therefore, it's very important that when someone is recruited to deal with color matching or any type of color assessment, that they are screened for normal color vision.
Thank you, ladies. That was very, very interesting. And indeed, I learned a lot of things today. But I have another question. Is there a difference when we examine a color or an object at a close distance? And is there a difference when we look, for example, at a building? What happens on our brain?
Well, Marina, thank you very much. That's a very good question, and I'm very happy you asked. You see, the back of our eye, our retina, is not uniform. When we look at something up close, we tend to gather all the rays so we can see the detail in a very small spot of the retina, which is called the macula. It's like a little pit. So what's so special about that part of our brain is that it doesn't have any rods, and it's very high density of cones, very nicely and tightly packed together. So whenever we want to read, for instance, something off a page, that's exactly where we focus the rays that come inside our eye. Now, so looking at something up close, we would judge its color, receiving a signal from that area of the retina. Whereas if we were to walk outside and look at a very nice building with a very bright, colorful facade, we would be looking at it from far away, and we would be stimulating a much larger portion of our retina in order to receive the signal for our brain to compute the color. Therefore, the answer is that a color may seem different when we look at it up close compared to far away, simply because a different signal is produced by the difference in stimulation of our retina.
And as I understand well, you said that we have 3 types of cone. How do they work together so that we can see all the colors?
Well, our brain does not interpret amounts of light. Rather, it can interpret differences, and it works in opponent channels. So the combination of the signal that is given from the red and the green receptors generate a response in our brain, which judges whether what we see is redder or greener. So there you have one opponent axis. The blue receptors in combination with the red receptors create a sense in our brain to interpret whether something is yellower or bluer, another opponent axis. And finally, the green receptors alone compute a signal that is interpreted in our brain, whether something is lighter or darker. So we have the cognition of three opponent axes.
Very good introduction to the famous color space that maybe some of you have already heard about. What is it, this Scilab space? Actually, this was built or computed to be able to put some values to the color. Because you've understood till now that everything we see is very subjective to each one of us. That means we need at some point to make it more objective, and we need to be able to evaluate it in a mathematical environment. And so the LAB space was created to try and reproduce what Cressida just explained of what is happening in our eye plus brain. And we will find again the opposition between the dark and black color on the L-axis. And then you've got this axis, which is A star, to compare the green and the red, and then the B axis to compare the blue and the yellow. And this is like a natural order of color, this color space, but it tries and fits to the perception we have of the color. And with that, all color can be placed in this space, like this red car or blue-green car or any other type of color. We can give them three coordinates, L star, A star, B star. And because we've got three coordinates with all of them in this three-dimensional space, then it is possible to measure an actual distance between them. So this is the delta E star that you've heard about, I'm sure, or maybe it's the first time, but at least now you will say you've heard about it. So the delta E is the distance between two color. And this is the combination of distance for the three axes, delta L, delta A, and delta B. And the space was built so that normally delta E equal 1 is the limit where below we don't see the difference, and above that we see the difference.
Now that you have explained that color space, can we place, for example, some RAL colors on it and see how they look?
So this is all the RAL colors.
Well, notice how the colors are sorted in this graph. The lighter shades are on the top with the higher L star values, and the darker ones are found in the bottom. The near gray colors are near the 0, point, and they are arranged from darker to lighter along the L star axis. And finally, the more saturated colors are found away from the 0, point of the A star B star plane. Now, the higher the A star B star values, the more saturated the color is.
And what happens when we have different textures and different effects of surfaces? We don't always have smooth surfaces. We might have surfaces that are textured, wrinkled, embossed, or even metallics, high and low gloss. What's going on then?
That's a critical question, actually, and very good that you raise it, because we really need to understand how the light is interacting with the matter in terms of optics. So how the light enters or not in the matter, how it is diffused, reflected by the matter, to understand how we can measure them. So let's go and have a look with some schematic way of explaining things. Let's take a smooth surface, which would represent, for example, a very high gloss surface. With this kind of surface, we've got what we call the specular reflection, and this specular reflection is like the part of the light that is directly striking the surface and does not enter into the matter, but is reflected the other direction, okay? And this is a small portion of it, like 4%, that is reflecting in the opposite direction. And then you've got the rest of the light, the rest of the energy of the light that enters into the matter, interacts with the pigment, and part is absorbed, if you remember, and the rest is reflected. And it is reflected in all directions. That's why we call it the diffuse reflection. And that's really the part of the signal that bears the color signal. So that's what we are interested in when we have to look at the color. But now, if we consider the same shade but low gloss. What happens when we as paint producer, we have to do a low gloss paint? The only difference between high gloss and low gloss is that we will add some matting agent additives in the paint. And what does the matting agent do? It migrates to the surface and it creates like a rough surface. So it destructurates the surface, making a microscopic texture. And it's exactly the same behavior if you have a grainy paint. It will be macroscopic, but the behavior with the light will be the same. What happened in that case? Well, we still have the diffuse reflection coming from the reflection of the pigment that goes in all directions. But what about the specular reflection? You've got some rays of light that would behave exactly the same way we have explained. But if we take another one, what happens? We see that now the specular reflection is going in the opposite direction, but it's totally different because it falls on another part of the grain, let's say. So if we combine it all the way along the surface, then the specular reflection becomes diffuse and is mixed together with the diffuse reflection, the color of the object, which means you are adding some signal to it and you are adding some whiteness. That's why when we look at a low gloss object, we've always got this impression of a milky aspect of the surface. And this is even more obvious when we look at dark color. If we take a full dark paint, well, all the diffuse reflection disappear because the black pigment will absorb everything. So the only thing that remains is the specular reflection part. And in that case, because you diffuse it in the case of the matting surface, then you will always have this energy that is diffused that makes your black not black anymore, but gray. So just people don't ask for a low gloss black paint that would be a deep black, because it's just not possible. The deep black is necessarily high gloss black. And this is an example of it, where you can see on the left part the high gloss black, which is deep black, and the low gloss one. And the only difference between the two is exactly the same amount of black pigment, but just you've got matting agent destructuring the surface. So we have to be very careful when we compare samples, that all samples you are comparing are at the same gloss level, because else you would maybe make some mess in the way you are interpreting the color you are seeing. And this is also to be taken into account when we want to measure it. So to keep going with answering to your question, Marina, I will give the lead now to Cressida.
Okay, so let's see how we can measure color. Now, as we mentioned, color is a physical experience that takes place in the mind of an observer. So measuring it straight from there is practically impossible. What we can do, though, is quantify the physical parameters that create this experience of color in our minds. Now, a spectrophotometer is a device that measures the ratio of reflected to incident light on a surface at many points in the visible spectrum. The angles and method in which a sample is illuminated can affect the observed color. Therefore, the geometry of a color measurement instrument is an important factor when choosing one to measure our surface. There are two main types of geometries: diffuse geometry. In this case of diffuse illumination, a sample is illuminated diffusely by an integrating sphere. Now, this provides for a general purpose color measurement instrument, and it is preferred for color matching prediction as it minimizes the effects of surface texture and appearance by the sample. In addition, we can perform measurements with integrating spheres, which allows us to include or exclude the gloss component that is produced by the surface. A 450 geometry is always gloss excluded, and it's a better simulation of the way that we perform visual assessments. Therefore, it is preferred for quality control applications.
Thanks, Cressida. Maybe we could also wrap up on that, saying that at least the sphere, even if it's further from the eye, it allows you to have like an average measurement of the surface. So when you've got a grainy surface or something textured, it would be a bit more easier to get something average and less sensitive to where you measure your sample actually. But saying that the 45-0 is closer to the eyes is true because we cannot combine all the direction all together. But still, it's a bit restricted. As with my eye, what I would say, or what I would do is I look at the sample not only in one direction, but I would move it to have a look at different directions. So then I think it's important to introduce the other geometry that allows that.
You're absolutely right. We can always use a multi-angle spectrophotometer. Now, this instrument illuminates the sample again at an angle of 45 degrees. However, it measures the reflected light at multiple angles. Newest models that are in the market today report that they can measure at even 12 different angles. Therefore, this type of instrument provides measured color coordinates of a sample as if it was moved back and forth, as you say. Just as you would assess it. And it is used especially for samples with coated pigments and special effect colors with additives such as mica or pearlescence.
Oh, that's all very interesting. But as far as I understand, we are going to see that all these interactions by all these elements together might sometimes be tricky. Isn't that right?
Yes, and let's start with the light for that, because first trick you might have already been confronted to is, well, what is the light above your head? And when you have to look at samples, you have to be careful with that because, okay, before Cressida presented the daylight light, okay, quite current, you go outside, you compare your sample and you're happy with your sample, right? And then you come back to your office. And then in your office, it's not incandescent light anymore because it does not exist anymore in the market. But most of the time, it will be like fluorescent light or maybe LED. And the distribution of the energy is totally different in that case. Both appears white, but don't be tricked. It is not the same white. And so it will not render the color the same way. Like the samples you have agreed on under daylight. Now you are back in your office and suddenly you say, oh, no, I will never accept this color. What have I done? I was not looking correctly. Well, you were, but you did not have the same light above your head. And now you've got a light that has peaks of energy, especially in some part of the spectrum. And if you've got a very small difference between your two samples, exactly on this part of the spectrum, then this difference that was not seen with daylight is become obvious now with the fluorescent light. And well, is the sample okay compared to the master or not? It depends. It depends on the application. It depends if it is for a building that you would put outside. D65 is enough. You don't need to accept this color under fluorescent light. But if it is a paint that is used internally in an office or whatever, it will be looked with some exterior light and some internal light. And in that case, you need to be careful that your quality control is adapted to your final application. And also you need to be very careful that you are assessing color in a controlled environments, such as light booth, where you can really say, okay, now I want to see it under daylight source, or I want to see it under fluorescent light source. And you are sure that you don't make any mistake in the light around you.
A few years ago, I was given by a customer a sample. It was a powder-coated sample, and he requested that we matched it in a coil-coated material. So we worked hard with a coating supplier. We matched it. We knew that it was a building, so we examined it under a daylight. And the customer, and also under artificial lighting, it matched. But the customer went inside the shop and in his office, and he examined the sample and it didn't match. Is that the same case that you're explaining right now, or it is something else?
Yeah, it's even going further, actually. It is what we call metamerism. And what is metamerism? This is what you just described. Two samples could appear exactly the same under one specific light, but in the end, when you change the light for something very different, then you would see a difference. And that comes directly from the pigment itself. So especially when you are comparing a powder coating compared to a coil coating, this is not the same pigment most of the time. And so we are not always able to reproduce, to match exactly the spectral curve. In this case of this green, if we measure them, then you can see that the curves are not so far one from another, but still they are not the same, so not the same pigment. And the issue here is, how is it that we see it the same under daylight? Because it's not the same pigment, we should not see it the same. But yes, just remember that this is here physics. We go from a spectrum that is infinite number of values between 400 nanometers and 700 nanometers. And with our eyes plus brain, we combine it into 3 axes only. Remember this red opposed to green, blue opposed to yellow, and this black and white axis. And so we transform n values or an infinite number of values in 3 values, which make it not unique transformation. And sometimes if the spectrums are close and you send an energy that is quite flat, then you would see exactly the same with your 3 types of cones. Where if you suddenly send the fluorescent light that is illustrated here by the F11, you start to see a very large difference on the A-axis because you put emphasis with the peak of the light on this part of the spectrum where you see much differences. And in that case, your cones start not seeing the same thing. So just be careful. But again, as you were mentioning, this depends on the application. This was for a building. So does it really matter if under fluorescent light it does not match? That's the question. And even going further, because here it was the interaction between the light and the object. If we have a look at the object now, and this is also interacting together with the light and the observer now. What would you say, Marina, Cressida, if I ask you to describe this color?
As we are in a coil coating seminar, I believe it's a coil coated sample, wrinkled, I think, where it's orange actually, but where the light reflects differently, we see something that's slightly yellow.
I would say it looks like an orange with a yellow orange peel effect.
Well, you're a bit too lucky because you knew already what I was going to show after that. And yes, actually, the color is just orange. Okay, so the color coming from the pigment of the object itself, it's just orange. The rest of it, what we perceive as being yellow or dark orange or light orange, comes from the shape of the orange, the reflection of the light. But this is just an orange color playing with the shape and with the orange peel that we don't want to see on a coil coating paint, but for an orange, that's fine. Yeah. So that means what? When we observe a color, what we do is we combine together with the color itself, linked to the pigment, we combine as well all the geometrical components of the object, like the gloss, the opacity, the shape, the texture, what we know of the object. So we've got our own interpretation. Don't forget that the spectral has no brain, and it does not interpret that this is an orange. That means if I go back here, this patch would be read as just an average orange, and that's it. So there is still a limitation between what we interpret with our eyes and what the spectral is able to read. That means with this kind of samples, textured effect samples, and so on, the spectral will help, but still our visual assessment is very important. Now, let's go a bit more into the observer side. Marina, can I ask you to look at it and fix your vision at the center of it? And well, for all you participants, I think you still start feeling something as well.
Well, I see the picture moving in circles, indeed, and it makes me dizzy also. Although we had an earthquake actually here in Greece, but
I guess, yeah. Well, it's not moving. It's a fixed image, and you have to trust me, even if your brain doesn't trust me. And it's just the brain that tricks you, okay, and builds something different. And we cannot always rely on what our brain says, and we don't even notice that, but it's in our daily life, and we're going to see some example of that.
That's right, Virginie. The way that our brain interprets the incoming signals from our visual system is quite complex. Now, we won't get into much detail, but we are going to talk about a couple of things that are important to keep in mind when we make a visual assessment between two samples. So number one, the background is extremely important. Now, please examine in this slide square A and square B. Square A is surrounded by white tiles, whereas square B by darker tiles. Now, what happens if I put B next to A? Voila! B and A are actually the same gray color, but our brain takes into account the background surrounding of each square in order to calculate their final appearance. In the following slide, we can see a cube. And if we focus on the, let's say, orange tile in the center, it is designed to be under a shadow. Now, would you say it's lighter or darker as compared to the center tile on the top that appears brown?
I know the image, but I see it later for sure.
Yeah. Well, let's see what happens if we put them next to each other. Well, they're actually the same color again. So our brain utilizes multiple information each time to compute the appearance of the specific color we're looking at. So by keeping a neutral gray background in a viewing cabinet when we assess two images side by side ensures that what we will judge will be accurate. Therefore, our recommendation is that always judge two samples side by side within a viewing cabinet under fixed lighting conditions, neutral gray background, and with nothing else inside the cabinet, because sometimes we put the samples and then we might leave our keys or we might leave something else, that might be a bright red color next to it. That can really obstruct the result of the visual assessment.
Okay, now that you said everything, it looks like it's a little bit difficult to achieve what George Orwell says. Happiness can exist only in acceptance. Or we can use this saying as a tool in order to set up some standards, tolerances, and procedures for our business. What do you think?
Yeah, I would say that if we go into the whole chain, then we have to agree, indeed. And me as a paint supplier, well, I would just sell the paint to you, not me, but okay, people around me, my colleagues. And then it arrives to you.
You have your tolerances, and then it goes to the coil coater. The coil coater should coat the material and deliver it to the building, adding also, again, another, let's say, tolerance. And also it has to do with the intended use and whether we should put side by side two things, to coated materials, or they are separate materials. And again, in the end, we have the observer, which he also has to his part, because he's the objective part, the subjective part.
Well, in this case, then we are focusing on the colored object part of the triplet that initiates the sensation of color, and that is what we try to control in our production.
Now, we can. I want to ask you something, Virginie. What would you say if you had this car and you had two parts side by side? Would you be able to accept any tolerance, any visual tolerance between those two parts?
No, for such a car, especially that expensive, I wouldn't accept any perception of difference, even if it's plastic parts and then coated parts on steel or whatever. It has to be exactly the same. So as soon as I see the difference, it's not acceptable.
If we had two different cars, for example, what would you say?
In this case, it's a bit different. Maybe you can have two different batches of paint, because in that case, you're never going to have the two side by side exactly. So the appearance of it will just look like the same, even if there is a slight difference. So I would accept some higher difference, let's say.
And if you had, for example, a handful of nuts or chips,
Well,
would you?
yeah. This is like the opposite example you are taking here, because I would expect here to have some differences, because all the same color, I would not eat them. But meaning that here, the tolerances that I would accept would be higher than the difference that I can see, and I can accept more than that.
So we see that depending on the intended use and on the customer perception of the materials that we provide, it changes also the level of acceptability that we are allowed to accept.
Exactly.
And going further to that, in order for us to have a guide in order to build the color tolerances, we have to take into account actually three factors. The first one is the intended use, and also this differs also. Let's take us, for example, this building. This building is a 3D facade where you can, even if you have the same color shade, it looks different because the light reflects in a different way. So if you were thinking of having exact color acceptance or exact color consistency, it would be in vain. Nobody could distinguish that. In the next case, where we have a building with glass windows, again, it would be very, very difficult to distinguish two parts that are not exactly color consistent. But on the third case, where we have cassettes side by side, we could not accept something less than total, at least visual color consistency. Now, moving on the next factor, ECCA has built for many, many years standards. The main two standards are EN 1396 and EN 10169, where also the color tolerances are included. So what is acceptable and what is not? And this can be, Cressida, would you like to comment on that?
So, of course. So this graph sums up basically the guidance that we have for our tolerancing. In the center of this graph, it's a delta B, delta A, delta L plot. We see with a red dot our standard. So we set our standard color, and then we plot all the batches that are produced around this color. Now, in the surrounding sphere is the tolerance that we have set for this color. And it's a very simple way to screen whether our production was within or out of limits of our tolerance.
Now, the next.
Yeah,
okay.
Go ahead.
The next factor is the agreement between the customer and the supplier. So what would you say, Virginie?
Yeah, this is very, very important, and actually, you have to agree at all levels of the production chain that was introduced by Terry. And of course, if you want that the final agrees on the color, that means the higher you go in the process, so at the first level, then the tighter the tolerance are getting. But still, you need to come to an agreement that is acceptable for everyone, and also for the capability of the measurement system, the production system, and so on.
And that is the reason why all the standards include as a final, let's say, sentence. Of course, the tolerances can change, and it depends also on the acceptance of the customer and the supplier.
Mm-hmm.
Now that we said everything, how and do we have any tools in order to measure that also online during production? How can we control color?
Yeah, because this is very important to make sure that the color is not deviating in time while your coil is moving and going on, and also that you're not deviating on the left part or right side of your band and so on. And there are systems that allows you to make automatic measurements directly at the output of the oven inline. And this is great because you can do real-time color monitoring and taking into account as well that the surface can be hot and maybe the color has changed, such as a bright red, you know, that when it comes out of the oven, it's like orange. This kind of instrument takes that into account. So that makes you, that gives you the possibility to really have accurate data, short-term, long-term, even if it is in very difficult environment, because this is built for that. So this is the kind of tool you can use in production.
Okay, and if we want to control our production, what tools do we have? How do we do it, Cressida? Do you have any idea?
Okay, well, I'm going to talk to you about color difference formulae. So let's take a minute and really analyze what it is all about. So suppose we have a standard color, in this case a gray, and we are comparing it to one of our production batches. Now, when we compare the two, we are set to make a pass or fail decision that will determine the course of our production. So one way to make this decision, obviously, is by visual assessment between the two samples. This, however, is subjective, time-consuming, and can be affected by other factors such as fatigue. It is desirable to make this pass or fail decision objectively via measurement, that we measure the two, standard and batch, using a spectrophotometer in which the software will calculate, using a mathematical formula, a pass or fail measure between them. And that is what the color difference formula does. Now, it's the most essential mathematical tool that enables us to make pass or fail decisions in industry, and it should correlate to the perception of an average observer. The most common we use today is the CLAB Delta E 1976.
So is this formula enough? Does it perform well? If we had another color shade, would it look like the gray?
Well, there are some cases that for certain colors, the outcome of Delta E star 1976 does not correlate well, cannot represent a visual assessment. And this is because though CLAB is a mathematically uniform color space, our vision does not interpret colors equally for all the hues. So we have chances where a very saturated blue, for instance, will match visually if we put them side by side, but when we measure them, the color difference will be above 1, which will lead us to a rejection, most likely decision, a failed decision. Luckily for us, research has developed, and let's see why this is the case. Now let's take this blue color and plot the AB coordinates in CLAB. Now if we plot a circle around the standard, which has a radius equals to 1, then it represents all the points within the boundaries of the circle that would pass the measurement. On the other hand, if we plot an ellipse that represents all the points that would visually match to us if we put them next to the standard, we can see that it also includes points that are outside of the circle. So as you can see, the traditional color difference delta E cannot account for those factors that influence the perceived color difference, such as hue and saturation. Now, luckily, research has evolved, and we are presented with a new mathematical color difference formula called CAD 2000. Some of you may have come across it. It is reported, but most modern software out there. It is more than a Euclidean distance over color space. So it allows us to measure how different two colors appear to our eyes. So it considers factors like lightness, chroma, and hue to determine the overall color difference. So utilizing it is more likely to give us results that will correlate to visual assessment, where delta E fails. Now let's take a look at some examples Now I have three different colors. You see that on the left we have a gray, where delta E and delta E 2000 are quite close with each other. In the middle we have a red shade, and you can see that the delta E 2000 is very restricted compared to the shades that would pass. And similarly on the left with a blue shade.
Very good. So if we wrap up on the delta 2000, we could say that this is a result starting from the fact that we have we've just noticed that the syllab space was not uniform and that it was not a circle that correspond to our sensitivity, eye sensitivity, but we needed to improve that according to the angle of view and to the saturation of the color. And so several mathematical equations were tried or were computed until this famous delta 2000 that is still today the reference for the CIE. And even though in paint industry, most of the time we are using CLAB, which is back to 1976. But the delta 2000 is really far better correlation to visual acceptance.
Well, this is very, very nice. And if you remember well, we presented in the beginning the color sphere, where it represents all the production batches of one specific color shade. And in the middle, we have the standard, which is the red dot. Well, actually, if you cut the sphere, you can see the plane of all the batches in A and B, and you can see that they represent actually an ellipse, like the delta 2000 that you actually explained. So, if we take that into account, I would also like to play a little bit a small game. Let's we say that we have a production run and we have a standard, which is this one, and we produce an actual production batch, which has a delta E of 1, and it is slightly deviated to the right of the axis. And then after that, we have another production batch, which is at the other side, slightly to the right side. So what will we see, Cressida, after that? If we want to compare the two of them, would they match?
Well, we must always match against a specific standard. Let's see what happens when we put these two ends side by side. Most likely, as in this case, there's going to be a mismatch, because there are exactly two batches that are acceptable from the center of our standard. However, the distance between them is too far away. This is why it's extremely important when making a comparison to be from a specific standard and not comparing batches side by side.
Okay, this happens in the lab and in the industry and in the factory. What happens in the real building? Let's see a picture of a real building now. And I'm going to change one cassette to have a delta E1. I bet that you cannot distinguish which cassette it is.
No.
If we go to a delta E3, can you see it, Virginie?
Slightly, but yeah, not that much.
And delta E5, now it's obvious.
Now it's even more obvious.
7 and 10. So you can see that in the actual world, sometimes, depending on the color shade and the light, you might not distinguish it. For example, here under a cloudy sky, we can also change the cassette, you don't know which, to delta E1. I bet you cannot see it now. But if we go further, delta E3, you can see it. We have also the example of 5 and 7 and 10 for reference. Let's go on. Cressida, do you see this building?
I was going to ask you, what is this building? Why are there so many different shades?
Actually, it's exactly the same color, but the orientation of the building sides are different, so the light reflects in a different way. Because of this color is metallic, this phenomenon is called flop. Virginie, would you like to explain a little bit about this flop?
Yes, very quickly, if we go into the attributes of the metallic paints, you would have a mix many times, maybe not natural metallic paint, but you would have a mix of color pigment, which is the diffuse reflectance, and the metal flakes, where you have specular reflection here, not as a mirror, but very close to a mirror. And in that case, when you are looking at a steep angle, when the light is coming directly on the sample, then the amount of light will appear very black compared to if you are looking at the direct reflection of the light. And this is what creates the flop. And this is where it is very, very important when you coat such paint, whether we are paint supplier or coil coater, we have to make high care on the way the flakes are placed on the coating. They have to be very flat, or always the same positioning from batch to batch if you want to keep consistency in the flop.
Now I have a question. Let's say I'm the final customer and I have a sample and I come to you and I say, I would like this color. What is the procedure?
You hand me the physical sample and I cooperate as a coil coater with my paint supplier. We provide the laboratory batch, we match the color, and we provide also samples. The samples, the laboratory samples, have to be at least 3. One goes to you, the other one stays with a coil coater, and the other one goes to the coating supplier. So this sample has also on it specific color, gloss, and thickness target values, as well as their tolerances, which are defined and mutually accepted by the 3 of us. So if the customer accepts that, we can proceed on to the actual production run, and then we judge the production run against this laboratory sample for the very first production run. If we want to repeat this production run, then we don't judge against the lab sample, but we take the first production, we name this first production a standard, and then we can move on reproducing this specific color again and again, having set a standard which is suitable for all of us. So today, I hope you had all an overview of color and how it is translated to our business, both for a coating supplier up to the final customer. We also learned that we have to be careful when we judge a color because there are a lot of factors that are affecting our judgment. And one of the most important factors is our own selves, our eye and our brain.
Yes, exactly. And this color subjectivity makes the colorimetry, the science of the colorimetry, quite tricky. And even though it is called colorimetry, so a metric of the color, it is not really a pure absolute metric. It's more an assessment of the color that will depend on the device you are using to measure and the environment and the type of sample you are measuring. So we always have to keep that in mind, that there are some limitations, even if it helps. And also, I think one thing that we should retain, well, everything we should retain for this webinar, but one that is very important is colorimetry is a very recent science. Newton started in 1666 to discover what was light and all these wavelengths, color wavelengths and so on. But the first real work on color organization, color space and so on started with Munsell only 120 years ago. That means this is a very recent science that still evolves today, and we need to keep evolving with it. That's something to keep in mind.
That's right. And we are very lucky today in industry because research has managed to produce some very good tools for us in order to take control of our production. And it's very important that the ECCA is up to date and the standards are being revised, including the latest color difference formula CIDD 2000, which is going to be included in the next standard. Now, color is subjective, but if we all manage to set some parameters correctly, we can manage things greatly.
We would like to thank you very much for your attention, and we are open to any questions you might have.
Hi, Ton, you have a question for the team?
No, sorry, it was
I thought,
a mistake. No.
no, not a question. Okay.
If you want to know more, we just invite you to come and meet us for the Congress in autumn, for the ECCA Congress. We will be there for a very nice workshop to go deeper into this topic as well.
And we promise that we will also have games for you.
So any questions for the team? I've got a simple one. Which are the most difficult colors to color match?
Who you're asking? All of us.
I'm asking the experts.
If you were asking me, I would say the lighter gray colors. That would be my answer.
Presentation.
And maybe some specific saturated color where you are at the limit of what you can do with coil coating pigment as well. Yeah.
Gray, a very bright green, bright orange, a purple one. Purple colors are very difficult for the coil coating industry due to the pigment. You cannot find the right pigments for them.
And also some of the bright color, sorry, just to finalize the answer, some of the bright color, I mean, if you really want this famous delta E below 0.503 for the paint supplier, then it's just nonsense because you don't need that. You don't see the difference, but you will do additional correction until you've got the color. And that's also some difficulties added. Yeah.
Okay, thank you. If I'm looking at the screen, is Beatrice, you have a question?
Yes, I have a question. If I'm measuring a sample and I send to another person to measure with a different equipment, what can I expect? I mean, if the spectrophotometer is a different brain and is a different technology, but I measure the same standard and the same sample, can I have any conclusion if we have different results? Or
I will take this one if that's all right with you.
Okay.
As long as you have the same kind of geometry, that's the first thing. Same geometry, so it has to be both spheres or both 450 directional geometry, then that's the first thing. And then you have to make sure you'd have the same level of instrument, like not a low range instrument and a high range of instruments, more accurate. When you know that, then even if you don't have the same brand of instrument, for most of the color, you will read exactly the same difference if you physically read the master and the panel. Now, if at some point you want to exchange the mathematical values, then this is where you really need to have exactly the same spectral, same brand, same batch of spectra, I would say, almost, to be sure that you can exchange the value and measure the same thing.
But if it is different geometry, I mean, one is angle and the other is spheric, but the samples are the same, exactly the same. I mean, can I see this is lighter or not?
No, it's just you cannot compare. You cannot compare at all the results, and this is because of the gloss that I have explained. One is going to include or partially include the gloss. The other one is going to exclude it, and you don't read the same thing at all between the two instruments. So that's the first thing to make sure of, that you have consistency with your customer on the geometry.
Okay, thank you very much.
Thank you, Beatrice. Any other questions on the chat? I can't see any at the moment. Okay. I guess in the interest of time, we'll start to close it now. As Virginia mentioned, we are planning to have a more in-depth workshop on colour in the Autumn Congress in mid-November. When you get a copy of the presentation, the exact dates are in the final slides. There are also some websites that you can visit or to access some more information on colour, the ECCA Academy and so forth. And if you've got any suggestions on other topics we should cover for webinars, then please get in touch with Eglin team. If there are no more questions, it just leaves me to thank the three ladies here, Virginia, Marina and Cressida, for putting together an excellent presentation, and I can see from the feedback in the chat that people have appreciated both the time, effort and expertise that they've used to put this presentation together. So thank you very much, and I hope you enjoyed it, and we'll see you at the next ECCA webinar